Tech-ni-shn here again. Today we are going to look at RF bandpass filters, and we will be testing for insertion loss, rejection, return loss and intermodulation. The bandpass filters are very important to provide the selection of wanted signals and rejection of unwanted signals, both in receivers and transmitters. If one wants to be more selective, i.e. higher Q, then one has to sacrifice insertion loss, as it also depends on the component Q. The rejection also depends on both the number of stages and the type of filter, and also the PCB board design. The effectiveness of the earth plane improves the ultimate rejection due to lowering the earth impedance. Early bandpass filter designs on PCB were often only single-sided and had mediocre performance. I've used the dual bandpass filter boards, which were available from kits and parts. They are unfortunately obsolete, but they may have some single bandpass filter boards. Also available, there are filter PCBs from QRP Labs and mini kits, or you can make your own. I'm using the dual band bandpass filter, and I have attached two relays to the other PCB which the board is mounted on, so I can switch between one filter and the other. If one is making a multi-band bandpass filter, such as 5 to 8 bands, then relays should be on every output and input to keep the isolation between the filters. It is also important to use good quality relays and check the isolation specifications. Otherwise, isolation can be degraded and you can start seeing the effect of other filters. Although I've used a kits and parts PCB, I've found the bandwidth, insertion loss and also return loss not suitable for my needs. So I've used values from QRP Labs. QRP Labs also do kits of filters as well as a relay switched filter PCB. When tuning filters, it is recommended to use something like a nano VNA, so one can look at return loss and insertion loss at the same time. I have found some designs have moderate insertion loss, but the return loss is very low, i.e. a high VSWR. The outer band return loss is normally also very low, and the VSWR is very high. If one can attain 15 dB or better in the pass band, then that is probably a good result, and with multiple stages that can be somewhat difficult. The size of coils or toroids, or even the material in the core or toroid, and type of filter determines the intermodulation performance. The equipment used is Siglent SSA 3021X, and using Easy Spectrum software, a 10 dB attenuator, the Rigol DG1062Z dual DDS generator. Sometimes I'll be using the HP8647 RF combiner and miscellaneous coax cables, adapters and attenuators. This setup here is for measuring the loss and the rejection using the spectrum analyzer into a external 10 dB attenuator, then into the dual bandpass filter. The output goes back into the spectrum analyzer. The test setup for looking at return loss uses an external return loss bridge into the bandpass filter, and the output of the bandpass filter is terminated. The output of the return loss bridge is fed to the input of the spectrum analyzer. If one wants to look at the intermodulation, then one can use the Rigol DG1062Z with two tones on separate ports into the two-port combiner, 10 dB attenuator for a good match to the combiner, then to the RF input of the bandpass filter. The output of the filter then goes into the spectrum analyzer. Alternatively, one can use the Rigol 1062Z dual DDS generator to generate double sideband suppressed carrier and use that to create the two tones. This is shown on the screen. Now I'll be checking the filter at both the 7 meg and the 14 meg frequencies. I have seen this double sideband suppressed carrier on other generators other than the Rigol. Believe a R1 type generator also has it. The image shown on the screen is of the dual bandpass filter. The relays are on either side. From the SMA connectors, there is a small coax which goes to the common connection of the relay, and then the switch contacts go to each relay. The relay on the right has a suppression diode, and a capacitor is on the left one to suppress any unwanted signals. I had previously normalized the screen to 0 dB at the top, and I'm now performing a test for the loss. The loss is approximately 0.9 dB at 7 megahertz, and by activating the marker table, we will look at the attenuation at other frequencies. At the IF frequency of 9 megahertz, there was only about 17 dB loss. That is insufficient, and hence the need for a notch filter. The next frequency, 16 megs, is what would be the oscillator frequency with a 9 meg IF. That is approximately 35 dB. With a low pass filter, then that will be further increased to perhaps 60 dB. The marker 4 is 42 dB. This will also be improved with the addition of a low pass filter for approximately 8 megahertz. I will now switch over and reset the markers for 14 megahertz. This is with the filter set to 14 megahertz. By switching the relay, the response, or the loss at the top, is approximately 1.3 dB. It is slightly over coupled, as you can see by the slight double humped response. I will now activate the the markers and you'll see the loss. The marker 2, which is a 9 meg IF, there is approximately 42 dB. The marker for 23 megahertz is the oscillator frequency, that is approximately 37 dB, and the marker for 32 megs is off the screen, and that is approximately 47 dB. Because of the filter is only a two-pole filter, the ultimate rejection isn't fantastic. It is adequate for the testbed, and with the addition of a low-pass filter for each band, then the image and oscillator rejection should be sufficient. This is the test for the return loss. We're looking at the 7 megahertz return loss, and in the pass band it is approximately 15 dB return loss. The next filter is the 14 meg filter, and this is it here. As I said before, it is slightly overcoupled with the dip, and the return loss isn't quite optimum. It varies between maybe 8 and 15 dB in the pass band, but it should be adequate for the test performed later. The next test will be the intermodulation test. This is the first test for the intermodulation. I am at 7.1 megahertz, and the difference between the primary tones and the third order tones is approximately 72 dB. If you divide the 72 by 2, you get 36, with the primary tone level being 0 dB. The output intercept is approximately plus 36 dBm. This is dependent on a number of things. The design of the filter. Some filters may affect the intermodulation. The other factor is the size of the toroids. The bigger the toroids, the less the intermodulation. Also, the material also plays a part, as I've found with some of the materials at lower frequencies, around 1.8 megahertz, there is a effect on the intermodulation. I will now reset the test for 14 megahertz. This is the intermodulation test for 14 megahertz. It is slightly worse than the 7 megahertz result, but the output intercept point is approximately plus 35 dBm, and with the loss slightly above 1 dB, the input intercept point is about plus 36. This figure is well above either the RF preamplifier input intercept or the mixer input intercept, so this filter isn't the limiting factor for the intermodulation.